welcome back to our video lectures on the course Material Science and Metallurgy. In today's topic, we will discuss the fundamentals of alloys, solid solutions and phase diagrams. This is an overview of today's presentation. First, we will discuss about introduction to alloys, then what is the necessity of alloying, then solid solutions basic terminology we will discuss. Already we have seen in the unit 1. Then we will talk about home rule 3 rules. Then what do you mean by solubility limits, and then we will come to the introduction to phase diagram. So before looking at alloy, so first let us understand what is a pure metal. So what are these pure metals? So pure metals are the ones which consist of only one type of atoms. So those metals which consist of only one type of atoms, then those materials are considered to be the pure in its form. So pure metals. So examples could be copper, aluminium, pure copper, pure aluminium, pure iron and pure gold, 24 karat gold, right? So these are the pure metals. But what are the limitations with, in materials perspective, what are the limitations with these pure metals? They are often found to be very soft in nature, they are too much ductile in its nature, and they are chemically very much reactive. They have limited strength, low wear resistance, and they may even corrode also. The pure metal can corrode. And they do not meet, because of these properties, they do not meet the mechanical demands of modern engineering applications. So, mixing of 2 or more materials has been practiced, and which we are calling it as alloying. So why we have to create these alloys? To overcome the shortcomings of pure metals. Just we have seen the limitations of pure metals. To overcome them, we need to create alloys to enhance the performance of the materials. So what is an alloy? So how do you define an alloy? So alloy is a metallic material which is composed of 2 or more elements where at least one material need to be a metal. So at least one need to be a metal. It will be combination of 2 or more elements, out of which one need to be a metal. Okay. So alloys, they may contain metals, and it can metals like copper, then iron. So they may contain these metals, or non-metals like carbon, and metalloids also it can consider. It can be composed, right? So what is the necessity of alloying? What is the prime reason why we are going for alloying? So obviously to overcome the shortcomings of the pure metals, the limitations of the pure metals. In addition, we need to improve the properties. We need to improve the materials properties in such a way that they are suitable for the mechanical property demands of modern engineering applications, right? So first, our intention is to improve the strength and hardness of the material. Then it can be to improve the corrosion resistance. Then it can be to improve the wear and fatigue resistance of the material. So we will be alloying it. Then if you are intended to improve the heat resistance of the material by adding the ceramic substitutes into the material. In order to tailor the electrical and magnetic properties of the materials as well, we will be doing the alloying. So alloying is being done because of these primary reasons. One, it could be for improving the strength and hardness. If we need to improve the corrosion resistance, then we can look for it. And it could be a wear resistance, or it could be a fatigue resistance, or it could be to improve the heat resistance of the material also. And to tailor, it could be reduction or improvement in the electrical and magnetic properties. If you wanted to tailor these properties, then also we seek for alloying of the materials. how we are doing it, how we are improving the properties. If we look at case by case briefly. So if you look at the property strength, how we are improving it. So with one example we will understand it. So strength is being improved by adding carbon and manganese to the pure metal that is a iron here in this example, iron. So for iron, by adding carbon and manganese, we were improving the strength of the material. Then corrosion resistance, similarly corrosion resistance. Similarly, if we take the same case of iron, by adding the chromium and nickel, two substances, we can improve the corrosion resistance, and that material we call it as a stainless steel. Stainless steel, it will be having carbon as a primary alloying element, and in addition to that, we'll be having more amount of chromium and nickel also will be present in the steel in order to improve the corrosion resistance of the iron. Then to improve the hardness, we are adding tin and zinc to the copper so that it will be forming bronze and brass. Right? If you add the tin to the copper, then it is a bronze. Then if you add zinc to the copper, then it is called as brass. Both these materials are considered to be harder when compared to the pure element that is a copper. Then conductivity. So if you look at the copper alloys, copper has been added with silver and phosphorus in order to improve the conductivity of the material. Further to improve, by default copper is a good conductor. Further, if you wanted to improve the conductivity of the copper, we will be adding alloying compositions like silver and phosphorus to the copper. Similarly, if you wanted to reduce the weight of the material, overall weight of the material, so aluminum alloys, in the case of aluminum alloys, already aluminum when compared to the other metals, it is considered to be light in weight and finds its applications in aerospace segment. Further, aluminum has been added with silicon and magnesium in order to further reduce the overall weight of the material. So which is considered to be aluminum alloy. So specifically, if we look at industrial applications in the segment of automotive industries, we often use the lightweight aluminum alloys. In the case of aerospace, we are using titanium alloys. In the case of construction, we are using the structural steel materials, steel alloys. Then in the case of electronics, solders, we are using it. So which is in high conductivity copper alloy and copper alloys also. In addition to that, high conductivity copper alloys also is being used in electronic industries. These are some of the specific applications of industry. Then if you quickly recall the term solid solution. So what do you mean by a solid solution? It is a homogeneous mixture, or it can also be considered as a single phase alloy, or it is a homogeneous mixture where atoms of solute element are uniformly distributed in the solvent metal lattice. So to the solvent metal lattice, these solute elements will be added to the solvent lattice to form the solid solution, to form a homogeneous mixture, which we are calling it, which will be having a single phase, and we are calling it as a solid solution, a single phase alloy. So what are the types of solid solutions? If you recall, we have seen substitutional solid solutions as well as the interstitial solid solution. So what are the substitutional solid solutions? And the defects in solids, we have seen substitutional case, substitutional impurity. So substitutional impurities causes substitutional, in short we can say that substitutional solid solution. So what happens here? Solute atoms are being replaced in the place of solvent atoms. In the place of solvent metal lattice, some of the solvent atoms are being replaced with solute atoms, and such kind of solutions, in that way the homogeneous mixture that is being created, that is considered to be a substitutional solid solution. An example could be copper and nickel alloy. Both have the similar atomic sizes, and same structure, crystal structure FCC, which forms substitutional solid solutions. Similarly, we have another solid solution, that is an interstitial solid solution. Just if you recall interstitial defect, so what happens? The smaller solute atoms will be occupying the interstitial sites of the solvent. If you are having the solvent something like this, so these are the interstitial sites. These interstitial solid sites have been occupied by the solute atoms, and by this way the solid solution that is created, that is an interstitial solid solution. It is called as an interstitial solid solution. So what is the example? Steel is the best example. So carbon is the solvent atom that is been occupying the interstitial sites of iron lattice. So in this way steels have been created, steels and cast irons have been created. So iron alloys are considered to be the interstitial solid solution, where carbon fits into the gaps of BCC or FCC iron, depending on the temperature. Then we have certain rules have been formed for creating, to form the substitutional solid solutions. Homotheory have been constructed certain rules where these are considered to be the conditions under which substitutional solid solutions can be formed. So let us look at what are these conditions. These are 4 key rules basically. So first one is the atomic size factor. The atomic radii of 2 elements should differ by no more than 15%. The solute atom radius and solvent atom radius, if you look at both the radii of 2 elements, they should not be differ by not more than 15%. Their difference should be well in between, it is well in within the limits of 15%. Difference should not cross more than 15%. That is the first condition. And second one is a crystal structure. It's about crystal structure. Both elements must have the same crystal structure. If the solvent atom is of FCC crystal structure, and the solute atom also need to be FCC crystal structure, right? So both should have the same crystal structure. Next one is electronegativity. So both should have similar electronegativity values, which helps avoiding formation of the compounds. Okay. Instead of forming as a compound, it will form as a single phase alloy, right? So both should have the similar electronegativity. Solvent and solute atoms both should have the similar electronegativity values. Then we have the valency. Both the metals or non-metal that you consider, which should have the same or similar valences, more likely to dissolve in each other. So if they are having the similar valences, they will be likely to dissolve in each other. So these first one is about the size of the atom sizes. That should be not more than, the difference should not be not more than 15%. And the rest of the 3 factors, one is crystal structure, negativity and valency, electronegativity and valency, both need to have same or similar parameters. Then once all these conditions are being satisfied by the 2 elements, so they are more likely to form a substitutional solid solution. Examples, if you look at copper and nickel is a one example, classic example. Then copper and zinc is also have found to be forming a substitutional solid solution. Okay. Then what do you mean by the solubility limit? Another term we often come across in the upcoming topics. So solubility limit. So what do you mean by the solubility limit? So solubility limit is the maximum concentration of solute that can dissolve in a solvent to form a stable single phase solid solution at a particular temperature. So it is basically a maximum concentration of solute that can dissolve in the solvent. If you take the example of sugar and water, so sugar is how much amount of sugar is being added to the water. It is having certain limit. So beyond that limit, the sugar cannot dissolve in the water. So it will be having certain limit, solubility limit. There is unlimited solubilities also. If we take the case of milk and water, so water can be how much water you added to the milk, it will dissolve completely in the milk. So similarly, alcohol in the water or water in the alcohol, so vice versa. So they also found to be having unlimited solid solubility. It's a liquid solubility. So here we are talking about the solid solubility. So it is a maximum concentration of solute that can dissolve in a solvent to form a stable single phase solid solution at a particular temperature is considered to be the solubility limit. So solubility is basically temperature dependent. If you increase the temperature, so maybe sometimes your solubility limit can be raised. Okay, more amount of solute atoms can be dissolved in the solvent. There are chances. That's why it is solubility is a temperature dependent. Depending on the temperature, the solubility limits will alter. If the solubility limit is exceeded, so you can expect in the system there is a second phase will be forming, which can be sometimes considered to be the precipitation, which is considered as a defect. Okay, and these precipitates also an advantage. If you can control these precipitations in the material, we can improve the property also, and we have seen in the strengthening mechanisms, right? So solubility limit, once it exceeds its threshold, then there is a chance that a second phase will form. Right? So what is the industrial relevance with this solubility limit? So understanding the solubility limit, if you look at it, understanding the solubility limit is crucial for especially heat treatment processes and designing a alloy, so material combinations and designing the alloy system. One need to have a clear understanding about solubility limits of the elements, two elements. And for the better heat treatment processes as well, the solubility limits will help us. Right? So next we will see the phase diagrams, introduction to the phase diagram. What is a phase diagram basically? So it is a diagram. Diagram is nothing but a graphical map. It is a graphical map or graphical representation that shows phases present in a system. Since it is a phase diagram, a graphical representation, that is nothing but a graphical representation where phases present in a system, a different combination of temperature, composition and sometimes pressure is being mapped. Okay, so that representation, that diagram is considered as a phase diagram. So it mainly shows the phases present in the system at different conditions or different combinations between temperature and pressure, or different between temperature, composition and pressure together. So it is overall a representation, a graphical representation, which is where phases present in a system can be discussed or represented at different conditions, like temperature, with respect to the temperature, composition and pressure. That is considered as a phase diagram. Right? What does it do? It helps us predict what structure will form under a given condition, under a particular temperature or a particular composition and pressure. What sort of phase or what sort of structure will form in the heat treatment process, we can able to predict it. So here the key terms that we come across throughout the metallurgy topic is, the first one is a phase. Phase, it is a region in a material with uniform physical and chemical properties. Phase is a region in a material with uniform physical and chemical properties. So phase is it's a little bit region in the material. So let us say you have the multi-phase or single phase. If you single phase is there is no another thing. So this is a one phase which is having atoms will be in one this thing. So it's considered to be the grain also sometimes in some cases. So grain, so you'll be having same atoms and where it will be having same or similar physical and chemical properties. It's a phase is particularly a region in the material where uniform physical and chemical properties can be identified. Then what is a component? Component is a chemically distinct part of an alloy. So component is a chemically distinct part of an alloy. It could be copper and nickel in a copper nickel alloy. So in the copper nickel alloy, if you consider, copper is a one component and the nickel is another component. Right? It is basically chemically distinct part of an alloy. Then system, it is a specific alloy or group of alloys under the study. So whenever we call the system, so we are talking about a specific alloy or a group of alloys which is under study, under investigation. So next, if you see the different types of phase diagram. So first, depending on the components, the working components. So we have three varieties of phase diagrams. So first one is a unary phase diagram where only one component, we talk about only one component, and basically this unary phase diagram shows the temperature versus pressure behavior of pure element, something which is the pure iron. So pure iron, the temperature and pressure behavior can be noted. So how the BCC and FCC phases are being present in the iron upon increasing the temperature. So the different phases of pure iron can be observed. Different allotropes of iron can be observed, like alpha iron, delta iron, the gamma iron. You can able to notice. The unary phase diagram, it is under the unary phase diagram. Even in the water, if you take the example of water is a single phase element. So at different temperatures and pressure, it can show different allotropes like water in the solid phase and water in liquid phase and the gaseous phase. Different phases also you can observe for the water. It's a single component system, which is the diagram which is drawn is considered as a unary phase diagram because it talks about only one component. Then mostly we talk about the binary phase diagrams where two component system is being considered. So it is most common in the metallurgy. We discuss more often in our upcoming lectures. So binary phase diagram, mostly it is drawn between the temperature and composition. On the x-axis it is a composition, and y-axis it is temperature, and here is the composition, x-axis. So binary phase diagram where pressure is kept as constant. So we draw the phase diagram between temperature and composition. Examples could be copper nickel system or lead and tin system and iron carbon system. Okay, eutectic system and eutectoid systems. We talk about it. We come across these terms quite later. We will discuss it. Then we have the ternary phase diagram where three components has been considered. So which is more complex and shown in a triangular format. Right. So just understand that there are three varieties of phase diagrams. Depending on the number of components that you consider, we can draw the phase diagrams for unary phase diagram, which are a single component system, and two component system, it is a binary phase diagram, and ternary composition is also ternary phase diagram is also there are more components. But the three components have been considered, which is more complex. What do we understand? So what information does these phase diagram will provide? So first one, it could be, obviously it talks about the phases at different conditions. That is how we have defined the phase diagram. And in addition to that, it can talk about the melting and solidification behaviors of the alloys. So what are the melting points for the different given conditions, and solidification points also it will give us. Then solubility limits of elements can be determined or identified from the phase diagram. Then certain reactions like eutectic, eutectoid, monotectic, all these reactions can be observed. We will see what are these reactions. Invariant reactions can be observed. Then basic information like phase composition and phase fraction at a given temperature and composition can be identified from the phase diagram. Then it can provide certain guidelines for heat treatment processes and which helps in designing the alloys system. Okay, so this is the information that we get it from the phase diagram. That's why it is very much critical to study and understand about the phase diagrams. What is the industrial relevance here as it has been given? So selection of alloys for casting process and welding, heat treatment and other manufacturing process, it helps us. The phase diagrams will help us. Then predicting the microstructure evolution during the cooling and heating processes, heat treatment processes, is very much possible. Then it ensures the mechanical properties based on the controlled phase formations. So by understanding the phase diagram clearly, we can control the heat treatment process so that the material that is being evolved through the process with certain properties can be very much controlled. So we can ensure the mechanical properties based on the phase formations. So in today's session, if we come to the summarize what we have discussed today, the key takeaways are this. So we understood that alloying enhances strength, hardness, corrosion resistance, and other properties. Certain combination of these properties or any one of these properties. Then solid solutions are the homogeneous mixtures where solute atoms will blend into the crystal lattice of solvent. We have defined it, seen the different types of solid solutions. Then we have seen certain rules for predicting the formation of substitutional solid solutions, the 4 rules of homogeneity. Then we have talked about the solubility limit, which defines the maximum amount of solute that can dissolve in a solvent to form a single phase alloy. Then we talk about the phase diagrams, which serves as the maps of phase stability, which helps in understanding the mechanical behavior during heating and cooling, is what we have understood here. So we leave the session with this quotation, like the key insight. So understanding alloys and phase diagrams is critical for designing materials with desired properties and predicting their behavior under service conditions. So one should understand the formation of alloys and phase diagrams, which is very much critical in designing the materials with the desired properties and which can help us predict their behavior under the service conditions. We have seen the classic case study of the Titanic failure. So there we have discussed how the failure conditions and all. So one should understand the formation of alloys and their phase diagrams. It is very much critical in designing the materials with the intended properties, and one can predict their behavior under different service conditions by understanding how, when temperature is lowered or increased, so what kind of phases are forming and how phase alterations are happening, and depending on that how the properties will be changing, one can understand it. So with that we will stop for today's lecture, and we will extend our lecture series on the phase diagrams. We will deep dive into the phase diagrams. So I have referred Callister as a textbook. You can also go through it. So thank you, and we will meet in our next class.